Hey, Swoo. Hi, Dr. Dean.
Good morning. How we doing?
Good, how are you?
Fabulous.
Oh, I want to tell me. All right, I'm going to call you back.
All right, so please remember to sign in and we will get started in a few as soon as everybody else gets in and on.
When is our exam?
You mean our next test?
Yes, sir.
So our next test is going to open next Friday. And for non-seniors, I mean, you'll have, more time than usual. But for seniors, since you're going to have to get your final and everything done a little early, I would suggest not waiting, but it will be up starting next Friday.
Okay, thank you.
Yep. Okay. So, starting off from last time, started talking about this idea of an index of refraction. So this is a number, again, that is kind of independent for every material. It is something that we kind of measure empirically, but it has to do with the speed of light traveling through that material. For air and a vacuum like space, N is usually just 1. But otherwise, it's defined like this, where the index is the speed of light divided by the speed, so the normal, I guess, speed of light, divided by the speed of light in that material, whether it's glass or water, whatever you're talking about. So a large index of refraction, a big N, means that V is very small, because when you divide by a small thing, you get a bigger value than if you divide by a large thing. We found some things that this indicates last time, because of the wave equation, where the velocity is equal to frequency times the wavelength. So we also discussed that with light, frequency remains the same. Okay. We didn't go too far into why this is. More or less, just basically took it as a given. So what we find is that the ratio of the indexes of refraction, N1 over N2, equals lambda 2 over lambda 1. So the index is inversely related to the wavelength. A large index means small wavelength and vice versa. So just remember that they are inversely related, not directly related. Okay. And you multiply these up, you get something that looks like this. Okay. So the idea here is that this is how light transfers between any two mediums. You could be going from medium 1 is air, number 2 is water, could be vice versa. But the point is that N times lambda is the same for any transition. It's always in lambda. And if you're talking about going from air to something else, you can kind of simplify this, because in air, N is 1. And to kind of repurpose this, the index of refraction of whatever thing you're talking about is equal to the ratio of the wavelength of light in the air and the wavelength of light in the medium. So this is how this index of refraction gets defined. Again, it's just the ratio of the wavelength before it goes through the transition and after it goes through the transition. What this brings up is that equation that we talked about that I throw on the board early on in the refraction, which is Snell's law of refraction. All right. So ignore all this for a second. So this is Snell's law of refraction. This is how we measure what happens with refraction. So if we draw our little diagram, so this is the interface. This could be air, let's say glass. So we have an incoming ray. And this angle is theta 1. So remember, we always measure these reflection and refraction angles from this center normal. And the outgoing ray, the refracted ray, so how this gets refracted depends entirely on the ratio of these two things. So let's look at theta for a second. What is the smallest value theta can be?
Is it 0 or 1?
So the smallest it can be is 0. Can't get any smaller than 0. Okay. So if it was smaller than 0, actually we'll go on to the next bit for a second. So what is the largest that theta can be? So what's the biggest value that we could have for theta 1?
One.
No. First of all, is that 1 degrees or is that 1 radian?
1 radian. Well, what about 2 pi?
No.
You said the biggest it could be?
Yeah. So let's draw a mini diagram. So we're talking about degrees for a second. Theta equals 0 degrees would look like what? What would our light ray be doing at theta equals 0 degrees?
Wouldn't it be like a horizontal line?
No.
Or would it be coming straight down?
It'd be coming straight in. Yeah. So let's do green, actually. Blue's a little close. So it would be a line going straight down. Okay. So what is the largest theta can be?
Infinity?
No.
Well, could the light be coming from like the side? Could it?
So like that.
So it'd be perpendicular.
Okay,
360.
what's theta?
90.
90. Why is that the most theta could be?
Well, I don't think light could come. Well, if you're looking at like if the sun was at the top, and you know how the sun go from what is it, west to east or something like that. You know what I'm saying? That's how I kind of was
So
thinking
you're
about
talking
it.
about the light source being over here versus
Yeah, then it.
over here.
Yeah.
Well, if the light source is over here, then it's going this way. And what's that angle?
90.
So it's no different. Okay, but why can't it be bigger than 90? So this is important to understand what exactly is going on, how the problem is set up. What if it were 99 or 100? What would that look like?
It would be like the light would be coming, I guess, out of that surface or like that line. You get what I'm saying?
It would be
And
coming
I don't
up.
think it can do that.
But that's not possible because we are defining the transition from this medium to this medium. If we did this transition, then theta would actually just be whatever that is, which if it was 100 degrees, this would actually be 80 degrees. So the point is that theta has to be between 0 and 90. It's the only situations that make any sense. Okay. So given that, what is the smallest value of sine theta? We have two options, sine of 0 and sine of
-1.
what is sine of 0 degrees?
Can it be negative
0? Is it 0?
0.
See, it's the same thing.
So sine of 0 is 0. What's sine of 90?
90?
Is it -1?
Not -1,
Positive one.
1.
positive 1. Yeah.
Thank you.
So the idea is if you have in one if you are going from let's say from air to glass, it's not the exact value, but I'm just going to say it is to make the math simpler. Air has an N of about 1. Glass has a, let's just say it's about 2. Diamond is closer, but we'll just go with this. Okay. So sine of theta 1 and sine of theta 2 are related how? What is something that we know about them? Rearrange that equation. Equals what?
What you say? What you say, Dr. D?
Is it 1?
It's not 1.
No, I was trying to see.
So given this, what does this equal?
You said, oh, but why
Is
wouldn't
it
it be
0?
It's not 0.
Would it be
-1?
2?
It's 2.
Oh man.
Divide this over. Divide this over. 2 over 1 or 2. So this thing is bigger than 1. This can only happen if the thing on the bottom is smaller than the thing on top by a factor of 2. So which angle is bigger? Theta 1 or theta 2?
Two.
2 is smaller
Theta 1 is bigger.
because sine of theta increases from 0 to 1 as the angle increases from 0 to 90. So a sine of a bigger angle is a bigger number. So in order for this to be 2, that means this angle is small. So this is Snell's law of refraction. And it becomes all about messing around with this little equation. Let's see if we can do an example. All right. Let's see. Don't want a crazy one. Don't want to break y'all's hearts. Okay. Let's do an example. So say light hits a diamond at 45 degrees. What angle does it refract? What is the angle of refraction? How do I start it off?
Are you talking about the angle go for 45 degrees?
What?
I said, are you talking about the angles of 45 degrees?
I'm saying, what angle does the light refract? So what law might I want to start out with? What relationship might I want to start out with? You gotta give me something.
Can you repeat the question?
So we're talking about finding an angle of refraction. What relationship or law might we want to use?
Newton's?
No.
Are we using sine?
The index of refraction.
Then
We're going to use the index or the indices of refraction, but there's a law that we just talked about.
Is it? Nah, is it the one with the N1 sine theta? Is it that one?
Snell's law of refraction might be a good idea to use when you're talking about refraction. Okay. What goes where?
Well, you know you got a 45-degree angle. So would that go in for theta 1?
Yep, so we're starting, the incoming ray is 45 degrees. Okay. Now what?
Would that say n equal 2.5?
So this says n equals 2.5, this says n equals 1.
Mm-hmm. So I'm assuming we would use those. I don't know.
Okay. But where?
So for N1, would you put 1?
Yes, because it's the refraction that goes with this angle. Right?
Yeah.
The
And then
purpose of the
N2 would be
subscript
2.5.
is that if it has a 1, then it's that angle is related to that thing. In this case, they're the ones on the same side. So 1 sine 45 equals
2.5.
Yep.
And then sine theta 2.
So what does theta 2 equal?
Sine at 45. Isn't that square root of 2 over 2?
So sine 45 is square root 2 over 2.
And then you could divide that by 2.5.
Okay. What would you get?
But then you can say square root of 2 over 2 times 2.5.
Yeah. So what's 2 times 2.5? What is 2 times 2.5?
Or 5. My fault.
Which equals 16.5 degrees. So if this comes in at a 45-degree angle, then this would be about 16 degrees. Okay, so this is refraction. This is how it's quite is about as simple as we can go with it. It's just solving this equation for the one that you don't have. So we've got two laws now that we can kind of start to combine and get some really interesting things out of. Let's see, trying to pull up on my notes. So diamonds are well known for being very shiny, very pretty. Part of that is this index of refraction being pretty high, but a big part of it, as most everybody knows, is the cut. So we're going to take these little laws here, and we're going to figure something out. So all right. Light comes in at a, we'll say 45 degrees again, angle. What I want to know is when it comes in, it's going to come off of there and hit this side, and it's going to bounce back. And it's going to hit this side, and refract back. Oh, I want to know, what is the final angle of refraction? So looks like a lot going on here, but we just separate it into different sub-problems. And it looks like we're going to have to do this on Monday. So I will redraw it, and we can go back over it then, because we've just got about a minute left. So it's a little much to start. But the idea is we're going to start taking reflection and refraction, both, and applying them to problems. Because one of the things that makes diamonds so shiny is the fact that there's a lot of reflection and refraction going on at the same time. There's a lot of stuff in everyday life that actually depends on both happening. So we're going to look at both happening together. That's all we've got for now. So you guys have a fabulous weekend, and we will see y'all Monday afternoon. And I'll be in the Discord office if anybody wants to chat or anything like that. So.